This is our third video covering the material in Chapter 2 on descriptive tables and descriptive graphs. Here we will talk about some descriptive statistics, both tabular and graphical displays for summarizing data across two variables, first using tables and then using graphical displays. When we have two different variables and we represent them in a table, we call it a cross tabulation or a crosstab. Sometimes these are also called pivot tables. A cross tabulation is a tabular summary of data for two variables. Crosstabs can be used when one variable is categorical and the other is quantitative, when both are categorical, or when both are quantitative. Of course, it goes without saying that if you have a quantitative variable, you will have to determine the classes yourself before constructing the cross tabulation. All of the considerations that we discussed in the previous video concerning determining the number of classes apply here as well. The left and top margin labels define the classes for the two variables in a cross tabulation. So here's an example of a cross tabulation from my Walmart data set again. I created this cross tabulation in a program called R, and I was interested to know whether or not there's a relationship between the price of fuel and whether or not the week includes a holiday. I was speculating that maybe there's more travel on federally recognized holidays, and that would increase the price of fuel. I chose three different bins for my quantitative variable, fuel price. The first one goes from $2.50 per gallon up to $3 per gallon, or $2.99 per gallon. The second goes from $3 to $3.50, and the last from $3.50 to $4. I chose percent frequencies rather than frequency counts for this particular table. My is holiday is a categorical variable, which is either true or it's false. What shows up in the table is the percentage of observations that fall within each one of the combined classes or categories. For example, 32.87% of the observations fall where fuel price is between $2.50 and $3 per gallon and it's not a holiday. 2.8% of the observations fall when the price is between $2.50 and $3 and it is a holiday, etc. It's common in tables like these to include sums of the columns and sums of the rows. These column sums and row sums are called the margins of the table, and interpreting them will be key when we get to probability theory and talk about marginal distributions, joint distributions, and conditional distributions. So the 35.66% here is equal to the 32.87% plus the 2.8%. And that shows me the total number of observations for which fuel price was between $2.50 and $3, regardless of whether or not it was a holiday. As another example, we can go and look at a row sum of 6.99%. That's the sum of the 2.8%, the 2.8% again, when fuel price is between $3 and $3.50, and the 1.4% when it is a holiday and the fuel price is between $3.50 and $4. So what this tells me is that 6.99% of the days fall, or 6.99% of the observations fall on a week where there is a holiday, roughly 7%, which we already knew. And that's regardless of what the fuel price is. So these are called the margins of the table. Converting the entries in the table into row percentages or column percentages can provide additional insight about the relationship between the variables. What I'm going to do here is I'm going to construct the percentage of observations that fall within each fuel price category within each class of week, whether it's a holiday or not, so that my row entries will add up to be equal to 100%. So what I've done here is I've taken each one of my percentages from the previous table, 32.87, 25.87, and 34.27, and I've divided them by the row totals. Recall that 93.01% of the days were not holidays, and 7%, 6.99% of the days were holidays. In that way, what I can tell is the percentage of days that fall within each fuel price category conditional on, or given that there is a holiday in the last row, or that there is not a holiday in the first row. This can be very helpful for uncovering relationships in the data. So carrying out all of these calculations, here is the final table. What I can see is that given that there is not a holiday, so conditional on no holiday, 35%, 35.34% of my observations are in the lowest fuel price category, 27.87 in the middle category, and 36.84 in the highest fuel price category. Now comparing that to weeks where there is a holiday, you can see that 40% of those weeks where there is a holiday are in the lowest fuel price category, and 20%, given that it's a holiday or conditional on it being a holiday, are in the highest fuel price category. So my original speculation that maybe holidays were driving up the price of gasoline doesn't seem to be supported by the data. And we wouldn't know this unless we were to do a deeper dive into the statistics and explicitly look at the relationship between these two variables. Summarizing data for two variables can also be done graphically. In most cases, a graphical display is more useful than a table for recognizing patterns and trends. Displaying data in creative ways can lead to very powerful insights. And the most common technique for looking at two different variables is to put together a scatter diagram that puts one of the variables of interest on the horizontal axis and the other variable on the vertical axis. And then oftentimes trend lines or lines of best fit are added to the graphs to help discern whether or not the relationship is a direct relationship where the two variables tend to increase together, no relationship at all where the trend line tends to be flat, or an inverse relationship where the increase in one variable tends to be associated with a decrease or a fall in the value of the other variable. Here's an example. Okay. We're going to do a scatter diagram. Okay, we're going to look at two quantitative variables this time. One variable which we will put on the horizontal axis, and the other variable we will put on the vertical axis. And then we'll look at the general pattern, and we'll use that to try to discern the relationship between the two variables. A trend line will give us a good approximation of the relationship. And we'll pick the trend line so that in some sense it goes right through the middle of the data. Exactly what that means statistically we'll go into great detail on later when we talk about regression analysis. And the only type of trend line that we're going to try to fit here is a linear trend line. So we're going to look at the simplest case. We'll look at other cases later in the semester. Here is a plot of my Walmart weekly sales. I put that on the vertical axis. And I put a variable called markdown on the horizontal axis. And a markdown is really a variable that measures the aggressiveness of a sale. So if Walmart, if a particular department is running a sale in a particular week, the markdown variable measures how aggressive that sale is. Okay. So it would appear that an increase in the markdown, or more aggressive sales tactics lead to greater weekly sales, because the line of best fit in the scatter plot seems to suggest that a bigger markdown is associated with higher weekly sales. Of course, this line of best fit doesn't fit the data perfectly. There are a lot of other things that determine weekly sales as well. Some of these values are quite far away from the line of best fit. But still, the overall association between the two variables seems to be a positive one, where increased markdowns do lead to increased sales. In order to truly identify the relationship between these two variables, however, would probably want to discover some of the variables and control for some of the variables that are causing weekly sales to vary in addition to the value of the markdown. Other ways of representing the relationship between two variables can be used if we have two categorical variables or even two quantitative variables that we have binned and determined the class width and the number of classes on our own. I'm going to show you a side-by-side bar chart and a stacked bar chart very quickly here. A side-by-side bar chart is a graphical display for depicting multiple bar charts in one display. And each cluster of bars will represent one value of the first variable, and each bar within the cluster will represent the value of the second variable. So here's an example of a side-by-side bar chart for two different sales departments in my Walmart data set. So the first department is in orange and the second department is in green, and I basically have two different dates that I'm comparing. The week that includes Christmas in 2010 and the week that includes Christmas in 2011. And I'm trying to discern both the overall pattern of change in weekly sales across time, but also compare the changes across these two departments. And it seems pretty clear that the first department has lower sales than the second department, whether I'm talking about 2010 or 2011. But you can also see that sales for the first department went up slightly between 2010 and 2011, while sales for the second department, while still higher than the sales for the first department, actually fell a little bit. So I'm comparing the height of these two bars to each other. I'm comparing the height of these two bars to each other, but I'm also comparing the height of the bars to each other within each year. You can see that there's quite a bit of information that we can see from this type of side-by-side bar chart. Another thing that we could do is we could stack the bars. This is a matter of preference because the information that we will see in the next bar chart is exactly the same as the information that we can pull from this bar chart. Here's an example of a stacked bar chart. A stacked bar chart is just another way to display the same information we saw in the side-by-side bar chart. It's a bar chart where each bar is broken into rectangular segments and they're given a different color. If percentage frequencies are displayed, all the bars will be the same height, leading to a maximum, of course, of 100% at the 100% mark. And here's an example for a stacked bar chart, which is not in percent, it's in weekly sales. You can see that by looking at the vertical axis here. The height of the second bar is a little bit higher than the height of the first bar. So again, I've got 2 years, 2010 versus 2011, and I have the same two departments. It's pretty easy to see from this graph now that overall at the store, sales have gone up a little bit between 2010 and 2011. It looks like the height here is a little bit higher than the height that's associated with the stacked bar in 2010. And it's also evident that the amount of sales in the first department has increased a little bit between those 2 years. And it looks like the sales in Department 2 probably has fallen a little bit, although that's a little bit more difficult to discern in this bar chart simply because the height of the two bars is just a little bit different from each other. So here's an overall schematic of what you've learned in Chapter 2. We've covered categorical data and the appropriate tabular displays and graphical displays for categorical data. The ones that are most important to me are the frequency distribution. It's not a difficult move to get to the relative and percent frequency distributions. Okay. And then for a single variable, we looked at bar charts. That was in the first video. And then we talked about quantitative data. And with quantitative data, I want you to know about frequency distributions, relative frequency distributions, percent frequency distributions, cumulative frequency distributions, cumulative relative and cumulative percent frequency distributions. We also talked about histograms for a single quantitative variable. When we talked about the relationship between two variables, they could be categorical, quantitative, or some combination of the two. We've talked about cross-tabulation. We've talked about side-by-side bar charts, stacked bar charts, and scatter diagrams.